In this lesson, we will answer the following question. How can we describe key attributes of the graph of this quadratic function in standard form by analyzing its equation? To graph a function of this form, called standard form, we can analyze the key features of the graph by factoring. Some key features of the graph include its x-intercept, the y-intercept, the axis of symmetry, and the vertex. So suppose we wanted to graph the following quadratic function by factoring. The first essential key attribute we're going to look at of the quadratic function is its x-intercepts. Recall that the x-intercepts of a function occur when f of x is equal to 0. So we can determine the x-intercepts of the graph by factoring to solve the equation f of x is equal to 0. So notice that by factoring this function, I can find that f of x is equal to 0 when x is equal to -3 or x is equal to +1, because this is just the factored form of our quadratic function. Since that's the case, if I'm interested in which x values make this function precisely equal to 0, then I'm trying to find a way to turn this factor to 0, and the only way to do it is to substitute in -3 for x. So if x is equal to -3, then this factor is going to be equal to 0, which makes the entire expression here equal to 0, since 0 multiplied by anything is equal to 0. For the exact same reason, we see that x equals 1 makes this factor equal to 0, which makes the entire expression equal to 0. So what this tells us is the graph of f of x intersects the x-axis when x equals -3 and x equals +1. And of course the output values of my function at those points is 0. So the axis of symmetry is a vertical line that's halfway between the two x-intercepts, which I've already plotted here. Here's -3, 0 and +1, 0. So the axis of symmetry is a vertical line that's halfway between the two x-intercepts, and it passes through the vertex. So the axis of symmetry has to be when x is equal to -1, because that's directly between the two x-intercepts. So the vertex is -1, since the vertex is on the axis of symmetry. And if I put -1 into my function, it gives me -4. So the vertex is at -1, -4. So here you can see I have graphed the x-intercepts, the axis of symmetry, which is directly between the two x-intercepts, and the vertex. So what I can do is now, to complete my graph, is I can find another point on the graph and reflect it across the axis of symmetry. So suppose I want to use the point 2, 5, since 2, 5 is indeed on the graph of this function. Since when I plug 2 in, I get 2 squared plus 2 times 2, so I have 4 plus 4, which is 8, minus 3, which is 5. So if I put a 2 into my function, I get out 5. So I know that point's going to be on my graph. Now what I do is I use the fact that the parabola is symmetric about the axis of symmetry. So if this point 2, 5 is on my graph, notice that this point here is 3 units away from the axis of symmetry. So I know its counterpart after I reflect this point across this line is going to be given by the point -4, 5. Okay, so we answered the following essential question today. How can we describe key attributes of the graph of f of x when f is a quadratic function in standard form by analyzing its equation? What we do is we factor the quadratic trinomial and solve for f of x is equal to 0 in order to find the x-intercepts. And then we find the x value that's halfway between the zeros of the function. Zeros is another name for x-intercepts, in order to determine the axis of symmetry, and we use that x value to find the vertex. To find the y-intercept, we just find f of 0.